Some of the most important technological challenges in electronics today are to build smaller, faster, smarter devices. This helps to make these devices more energy efficient, more portable, and to increase their overall efficiency. If we just think about how the scale of devices has changed over the years, over the decades PCs have scaled down enormously. Mobile phones, compared to the original invention, they're much smaller devices than they were in the early days. So we're working on a large interdisciplinary research project which is funded by the UK Research Council, that's the EPSRC. The project is designed to bring together a team of scientists to research the development of downscaling of these devices and the materials that are contained within the devices. The method that we're using to do this is a technique which is called supercritical fluid electrodeposition. Electrodeposition is a very well-known technique that uses a solution containing charged particles or ions. And when we apply a voltage, we can grow materials onto the conducting surfaces. This is an important aspect of the technique in that controlling where the deposition occurs is very straightforward. Moreover, we can use this technique to grow layers of different materials one on top of the other to create multi-layer structures. Depositing materials like metal nanowires is a very different challenge. The scale of these materials is difficult to achieve. We can control to some extent by using patterned electrodes, but when you get down to these very small dimensions, one of the problems is pore blocking. The molecules start to accumulate at the neck of the pore and prevent growth of the material. We hope to get around this by using supercritical fluids to conduct our electrodeposition experiments in. Supercritical fluids are fluids that behave like gases in that they're very mobile, but they also allow us to dissolve chemical compounds in them. So in that respect, they're much more like liquids. The important point from our perspective for our project is that they allow molecules to penetrate deep into the holes on patterned surfaces or electrodes. So if we combine electrodeposition with supercritical fluids, we hope to be able to grow lots of exciting new materials on a nanometer scale. For example, we are planning to work towards growing single electron transistors based upon 2 to 3 nanometer crystalline germanium nanowires. This will really allow us to break through some of the current technology barriers and advance the development of exciting and very small scale devices. To be able to achieve the aims of the project, we need to be able to prepare to make in the lab chemical compounds which will act as a source of the elements in the supercritical fluids. We also need to be able to create new types of nano-patterned surfaces that will allow us to conduct the electrodeposition within these. The performance of the materials that we deposit depends very much on their structure and their composition. In order to be able to probe these properties, we use techniques like electron microscopy and X-ray diffraction. These techniques allow us to determine the ratios of the elements, the types of elements that are present, and their positions within the structures. This is a really important aspect of our project to understand the properties of these materials. So this exciting project brings together a team of over 20 research scientists across a range of disciplines to tackle these challenges. We hope to demonstrate the full scope of supercritical fluid electrodeposition as a technique to produce devices and materials on a scale that's never been achieved with any other method.